Welcome to this explainer. Today we're looking at a massive architectural shift sweeping right through enterprise IT. Basically, we're moving from a world built entirely around human identity to one that must urgently secure autonomous machine identity, specifically AI agents. If you're experimenting with agents right now, let me tell you, the old static role tables, they're not going to save you. We need to talk about policy as code and how to build truly dynamic access controls.
Okay, let's dive right in. Here's our roadmap. We'll start with why agents are not humans, look at the unique risks they introduce, cover core access control principles, tackle real-world implementation challenges, and finally, walk through a 5-step playbook to secure your agents.
Section 1. Agents are not humans. The paradigm shift in identity.
So think about human access for a second. It relies on bounded login sessions, single sign-on, MFA. A human makes conscious, in-the-moment decisions, right? But an agent, it has absolutely no natural session end. It explicitly requires a time to live, or TTL. For humans, the policy question is mostly, who are you and what's your role? But for agents, that policy question has to be, who are you, who actually authorized you, and what specific task are you executing right now? Because honestly, an agent's identity alone tells you almost nothing about whether an action should be allowed.
Which brings us to AI agent access control. It's the set of policies governing exactly what an agent can see, retrieve, use, or change. This gatekeeper layer is crucial because it prevents the ultimate agent risk, the confused deputy scenario. That's where an agent is tricked into using its privileges for a malicious task, effectively utilizing way more privilege than the current task actually needs.
Section 2. Risks of autonomous AI agents. What happens when things go wrong?
Look, if an agent lacks clear boundaries, you are facing severe data exposure and unauthorized actions. But I really want you to pay attention to human agent risk inheritance. Credential theft is a human risk, sure, but if an agent simply inherits your broad human permissions and then gets hit with a prompt injection, it becomes a massive liability. It has all of your access, but literally none of your human judgment.
Section 3. Core Access Control Principles, from static to dynamic.
Now, to do this right, you really need to design around the NIST ABAC decision architecture. You're implementing policy as code using something like OPA, Rego, or AWS Cedar. You need a policy enforcement point, a PEP, intercepting every single request. That PEP asks the policy decision point, the PDP, to evaluate the rules. The PDP then uses a policy information point, the pipe, to pull in real-time attributes like task context and data sensitivity. And finally, the whole shebang is managed in a policy administration point, the PAP, where your policies are version controlled in Git, just like regular code.
Next up is least privilege by design. Your policy engine shouldn't just check static roles. It needs to evaluate the subject type, the intent, and the resource sensitivity fresh on every single request. An agent should hold only the access its specific current task requires. We never, ever trust the caller's own claim of authorization. And that leads directly into time-bound and task-bound privileges. Agents require short-lived, cryptographically attested tokens, essentially just-in-time access. Tying access to a specific duration is what prevents standing permissions from accumulating into this dangerous backlog of orphaned access. This next principle is an absolute game-changer: runtime validation. We don't just gate once at session start and call it a day. We continuously reevaluate on each sensitive action. You can actually feed risk-adaptive signals right into your policy engine, things like anomaly detection, unusual tool chaining, or behavioral drift, blocking actions dynamically as the context changes.
Section 4. Challenges in securing AI, the reality of implementation.
AI agents exhibit incredibly dynamic, unpredictable behavior across very complex supply chains. Because of this, relying on static access reviews, it's practically useless. Plus, agents introduce a massive untraceability gap. To solve this, you absolutely need an immutable signed audit trail where every policy decision is logged with the full attribute bundle. You have to be able to reconstruct exactly why a machine was allowed to do something.
Agents can access and change data way faster than any security team can manually respond. Your controls have to operate at machine speed. And because your policies are written as code, you can actually write unit tests for them. For example, testing that an agent with an expired credential is mathematically guaranteed to be denied, and then running those tests in your CI/CD pipeline before they ever hit production.
Section 5. 5 Steps to Secure Agents, the Production Playbook.
Okay, here is your operational playbook. Step 1.
Assign a distinct, attested identity to every single agent to track attribution. Step 2. Define strictly scoped, least privileged permissions. Step 3. Apply those dynamic, policy-based access controls. Step 4. Monitor and reevaluate at machine speed. And 5. Review and update continuously. The ultimate goal here is that access isn't a static grant checked once. It's a continuously reevaluated function of identity, task, and risk, with both humans and agents flowing through the exact same PDP, but supplying very different sets of attributes.
I'm going to leave you with a final, provocative thought here. Are your current access controls built for human speed or machine speed? If your organization is stepping into the agentic enterprise, it is time to drastically rethink your architecture. You need a framework to discover, govern, and secure AI agents well before they become a liability, which is exactly what platforms like Mimecast Agentic AI Security are built to do. Thank you so much for joining me for this explainer, and we will see you next time.